Welcome to an example of free undamped motion. We learned in a previous lesson that we can describe free undamped motion using these linear second-order homogeneous differential equations, where these three equations are equivalent just in a different form. So looking at this first equation, we have m times the second derivative of x with respect to t plus k times x equals 0, where m would be the mass, and then k is the spring constant, and x is a displacement. So let's take a look at the given information. We're first told a force of 400 newtons stretches a spring 2 meters, which means when F equals 400 newtons, if the spring is stretched 2 meters, we think of this square here as having a force of 400 newtons. The spring is stretched 2 meters, and therefore S, the spring elongation, is 2 meters. Well, from this information, we can use Hooke's law to find k, the spring constant, where F is equal to k times S, which means in this case we would have 400 equals k times S, or k times 2, which would give us 2k. Dividing both sides by 2, we would have the spring constant k is equal to 200 newtons per meter. And notice how we need k in our differential equation. Next, we're told a mass of 50 kilograms is attached to the end of the spring. So the mass m is 50 kilograms. And the mass is released from the equilibrium position with an upward velocity of 10 meters per second. So because the spring is released from the equilibrium position, that means the displacement at time t equals 0 would be 0. So we can say x of 0 equals 0, but it is released with an upward velocity of 10 meters per second. And because the velocity is upward, the velocity would be negative. If the velocity is downward, the velocity would be positive. So we can say x prime of 0 is equal to negative 10 meters per second. So let's go ahead and take this information to the next slide and set up our differential equation. Again, we found the spring constant k was equal to 200. The mass was equal to 50 kilograms. X of 0 was equal to 0, and x prime of 0 is equal to negative 10. Let's go ahead and use this form of the differential equation. So we have x double prime plus k divided by m would be 200 divided by 50 times x equals 0, which would be x double prime plus 4x equals 0. Now again, this is a linear second-order homogeneous differential equation with constant coefficients, so we should recognize that we can solve this differential equation using a characteristic equation. Meaning, if this is the form of our differential equation where a, b, and c are constants, this would be our characteristic equation, and then based upon the types of solutions, it would determine the form of the general solution, which in this case will have complex solutions or complex roots, and therefore our solution will be in this form here. So let's go ahead and set it up and show the work. Notice that a is equal to 1, b is equal to 0 since there's no x prime term, and c is equal to 4. So we would have r squared plus 4 equals 0. Subtracting 4 on both sides, taking the square root of both sides. Notice how we have r equals, this would be plus or minus 2i, or if we want, we can write this as 0 plus or minus 2i. So referring back to our notes for a moment, this would be in the form of alpha plus or minus beta I. So alpha is 0 and beta is 2. And since alpha is 0, we'd have e to the 0 here, which is 1, as well as here. So we'll just have c sub 1 cosine 2t instead of x, plus c sub 2 sine 2t. Again, this would be e to the 0, which would give us 1. Before we go on, though, I do want to point out one thing that you will see in some textbooks. Looking at this form of the differential equation, where we have omega squared times x, remember our omega squared would be 4, and therefore omega would be equal to 2. If we use this form to set up the characteristic equation, we would have r equals 0 plus or minus omega I. So again, using this form from the characteristic equation, this would be the general solution. So we could just use omega t here and here instead of showing the work for the characteristic equation, but I do prefer to show the work. Now we need to find the values of c sub 1 and c sub 2 from the fact that we know x of 0 equals 0 and that x prime of 0 is equal to negative 10. So using this first initial condition, this means x of t would be 0 when t is 0. Well, if t is 0, this would be cosine 0 or 1, so we have c sub 1. And then here we have sine of 0, which is 0. So this product here would be 0, leaving us with c sub 1 equals 0. So x of t must be equal to, if c sub 1 is 0, we would just have c sub 2 sine 2t. And now to apply the second initial condition, we'll have to find our first derivative. So x prime of t would be equal to c sub 2 times the derivative of sine 2t, which would be c sub 2 times cosine 2t times 2, or 2 c sub 2 cosine 2t. So if x prime of 0 equals negative 10, x of t is negative 10 when t is 0. So if t is 0, we would have 2 times c sub 2 times cosine 0, which is equal to 1. So negative 10 equals 2 c sub 2. Divide both sides by 2, we have c sub 2 equals negative 5. So substituting negative 5 for c sub 2 will give us the equation of motion, which is x of t equals negative 5 sine 2t. Let's finish by looking at the graph of our equation of motion. And here it is. Remember, when x of t is negative, here the mass is actually above the equilibrium position, and when x of t is positive here, the mass is actually below the equilibrium position. I hope you found this helpful.